to another edition of RCE. Again, this is Brock Palen. You can find us online in our entire back catalog at rce-cast.com. You can also find links to all the Twitters and the blogs and everything there. We can find other ways to get a hold of us. Also, please feel free to send in nominations for topics to have on the show. Also, we have Jeff Squyres here as always helping us out. Jeff, thanks again for your time.
Hey, Brock. It's another lovely spring day and another cool topic to talk about today. What do we got?
Today, this is actually something I ran into looking I think it was the NERSC website, and I was curious, okay, what the heck is this thing? And it is called SciDB, and so I will admit that the whole reason I dragged our guest on here today is because I want to figure out what it is. So our guest today is Paul Brown. Paul, why don't you take a moment to introduce yourself?
So hi, my name is Paul Brown. I'm the architect of SciDB. The firm I work for is the commercial wing, which is called Paradigm 4. You can find SciDB at www.scidb.org and Paradigm 4 at www.paradigm4, that's paradigm one word 4 one number.com. Paradigm 4 is the sponsor for SciDB, and I work for them. My background, I've worked for a heap of database companies that started with the letter I. So I worked for Illustra, I worked for Ingres, I worked for Informix, and I spent 10 years at IBM. And then when SciDB started up, I joined SciDB as the architect and general dog's body.
So what is SciDB?
It's a good place to start. So SciDB, it stands for Science Database, and you remember the name Paradigm 4 for the company. So the point of, or the motivation for SciDB was the work of the late Jim Gray, improving data management tools and technologies and platforms for scientists. So Jim spent a lot of time at Johns Hopkins working on Sloan. And SciDB was kicked off out of an XLDB, extra large databases research group. And my boss's boss, Mike Stonebreaker, and his colleague Dave DeWitt, spent a lot of time walking around and asking scientists what they wanted in a database platform. And it sort of broadened out a little bit from just databases. And we built SciDB to meet those requirements.
Now, when you hear the term database, we've all kind of been conditioned to think, relational database, SQL, and now there's these young upstarts, the no SQL crowds and things like that. Is SciDB fit in one of these two categories?
So the other thing about that word database is or database management system is it's much older than relational. And I suspect it'll be much newer than the NoSQL guys. It'll keep on going. So if you look back, we had hierarchical and network databases, we had relational databases, we had object-oriented databases, we had XML databases, and now we've got NoSQL databases. So SciDB it sort of continues that grand tradition of coming up with a new name. But the signature difference between SciDB and what's gone before is that we've chosen arrays and matrices as our building block for our storage manager and as the internal unit of data processing in our query engine. So think about SciDB. It's if you pick up a SQL database engine and you think relations, don't think relations with SciDB, think arrays and matrices.
So is there, internally, how do you guys do stuff though? Like, is it closer related to would you say it's more closely related to a traditional SQL database, a columnar database, or like a Vertica or something like that, or a NoSQL object store?
So think about almost all of the above. So the data model, and at the risk of doing a bit of a lecture here, so it's multidimensional arrays is the organizational principle. So every time you organize data, you store it in an array. And the array, each cell in the array, each logical position can have multiple attributes. So the first thing we do is like a column store, we just divide the database up into, you can think about it as one array per attribute. So it's a vertically partitioned data store. But the second thing we do is that we basically asked the boys and girls who've been doing array processing for 20 odd years, we said, well, what do you do with arrays? And they said, well, we chop them up into rectilinear partitions, We store the partitions separately. We might spread them out over a file system or divide them up into a collection of HDF5 files. And then we do parallel processing by organizing our algorithms to deal with the access to each of these subarrays, each of these rectilinear chunks, we call them, and then the sort of rotation or mutation of data around the nodes that make up your massively parallel system. So I guess the tensor is that, we're a column store insofar as we divide stuff up into one column per attribute of the array's cells, but then internally we organize ourselves in the same way that people have done big square databases before. Just we do transactions as well, so there's a database piece in there. When you update the array, we make acidic guarantees. And we have a query language that looks a bit like, if you remember, there was an old language from the late 60s, early 70s called APL. So when you manipulate the objects, you do things like array multiplies or filters or, array vector products, that kind of thing.
So, what you just said there gave me a lot of questions. So the first question, though, is you mentioned HDF5 and the fact that you're trying to store data a lot of the same ways that scientists may store data partitioned across a big, parallel job or some sort of data parallel job. Can you actually compute directly against data in SciDB using like the MPIO functions or something like that?
It's sort of the other way around. We pulled the MPI framework inside SciDB. So what you do is, supposing you want to do something like a big truncated SVD is a good example because we did that. So one of the things that we did in our design and implementation process is we wandered down to the North Carolina and we talked to Jack Dungera and we sort of said, okay, how do the boys with belts and suspenders do this for a living? And we learned from him how you do block cyclic or block partitioned algorithms for linear algebra. We learned how you do, block cyclic rotation of data through the nodes. We looked at his scalar pack implementation, the way it uses MPI, and we grabbed as much of that technology as we could, and we've reused it inside SciDB. So if you've got, a very large matrix, we do sort of 60,000 by 50,000 is the size that we sort of run into on a regular basis, and you want to compute the top two coefficients of a truncated SVD, that's the sort of operation you just directly ask. You say literally GESVD of array A, and we return your three arrays, your TVU, and you can figure out data from there. And we make it scale as best you can. They're all cubic algorithms in this space, but we make it scale by using as much of the hardware as it run on as we can. And I guess that the thing to sort of step back a bit is that isn't just that GESVD operation, general purpose singular value decomposition. It sits alongside a very large list of other, you might think of them as sort of more orthodox data operations. So, filters and slices and betweens and shape changes and dimension reduction algorithms and things like that. So the idea is to have this composable language, a functional language that combines high-level linear algebra operations with lots and lots of kind of low-level useful things, filters and aggregations and group bys and regrids, windows, that sort of stuff.
So this is interesting. So did I hear you correctly say that you actually use MPI inside the database? And so therefore your database infrastructure could actually span tens, hundreds, or even thousands of nodes, depending on how many clients or types of jobs you're serving simultaneously. Yep. Is that a goal of what you're going for?
Yep, exactly. So at the moment, our biggest sites have sort of 200 to 400 physical nodes. You can do an awful lot of damage with 400, modern Intel 16-core boxes with, 32 gig of memory on each of them. That's an awful lot of compute power. And we really purely because we just haven't had the capital, we haven't been able to push much beyond that. But there's no particular reason in principle, given the architectural design, that we couldn't. So again, sort of our background is I worked on high-end DB2, and I've worked on massively parallel Informix engines in the past, and it wasn't uncommon. It was a bit rare. We only